My name is Shyam Iyer. I am a distinguished engineer at Dell, but here I'm representing as the chair of the technical working group in SNIA called SDXI. SDXI stands for Smart Data Accelerator Interface. So one of the cool things about SNIA is, you could be working on an exotic technology like the DNA storage that the previous presenter talked about, and then you can also be doing things that are so fundamental that they need to be solved, right? And I'm trying to solve a problem, or a lot of us are actually trying to solve the problem of making memory to memory data movement boring. Okay, boring is a nice thing because when we do things stupidly simple, we can do interesting things. And that's one of the things. The problem is, for long, we have had a data movement standard, a memory to memory data movement standard, and that's software-based memcpy. It works because it has enjoyed a very stable instruction set architecture, right? Uh, the problem is it takes away from the application performance. It incurs software overhead when you're trying to provide isolation, whether it's virtualization or you want to just have like user kernel address spaces being different. Uh, Offload DMA engines are not a new concept. I mean, how many of you have worked with different kinds of DMA interfaces? Every time you have to write new software, new APIs, new memory structures, and we were getting a little bit tired of that. And there's no standardization at user level software being able to access these kind of DMA interfaces, right? And so the problem is also that we have new usage models that are emerging, which means that you might want it to copy a terabyte of memory, and when you're doing that, you don't want your CPU to be just doing that. You want to make an accelerator do this. Tell me when you're done, and then while you're doing that, I might be doing something more useful. So that's one kind of mark. You might also be trying to move the data into persistence and recovering that from persistent data, right? Now, you could say that you could do that because you have memory pointers, but why don't we let some kind of a memory accelerator do that kind of a job instead of having to spend the time in doing that? You might want to say that I have data in a virtual machine. I want to move that data to another virtual machine, maybe in the same server, maybe in a different server, but I don't want to copy that data through multiple layers of the software stack. If you're typically in a virtualized machine, you might do the data copy from virtual machines buffer to a hypervisor buffer, and maybe to another buffer to be able to do the DMA. And then you go through an IO device, go through the network, come back, and then do the same kind of copies all over again. How about we do this really simply, which is move the data from the user space buffer of a virtual machine, directly write it to a user space buffer of another virtual machine. Of course, do it in a very secure manner. That's the idea. The memory space is actually expanding. I mean, if you've been in the STC conference and you've been looking at all the CXL added memory space being added to the system physical address space, you have a lot more memory that you can deal with right now. And they're all different types of memory. So, sometimes the memory, it can take a long time for the data to come back, and it can cause a stall. You might want to send an accelerator to do the job of clearing this kind of memory. Something else that you might want to do is, as you're moving the data, how about we transform it? Something as simple as doing some kind of an XORing operation is a data transform, or you can do something like a compression or an encryption as you're moving the data from a source buffer to a destination buffer. And that's something that we would like to give that to an accelerator. Or you might want to compute the data while it's still in memory. So computational memory is something really interesting because you don't have to move the data too much to some other layers of your system topology and compute on the data while it's still being in the memory. So SNIA decided that, our work came together to form this work group, the SDXI technical working group. And the mandate was like, we'll make it extensible. We'll make it forward compatible. we'll also make it independent of an I/O interconnect technologies. I mean, I don't care. It could be pigeons trying to move the data, but it should have a standard structures to move the data, right? So it was formed in June of 2020. Almost 23 companies contributed to this spec, and we got the version 1.0 released November of 22, right? So that's really a fast turnaround time. It goes to how much this is needed in the industry. So the way we did was, we wanted to design the standard in such a way that the accelerator interface could allow you, as an application, direct user mode access, which means you don't have to deal with different layers of software, right? But you still want the stability of an architecture, and you also want the security guarantees while you're doing this kind of things. You also want to make sure that you can move data to different types of memory. So that's what the standard is trying to do. We didn't want to write the standard in such a way that only one kind of CPU architecture could make use of this. Because if you wanted to use specialized instructions just to be able to do the data movement, then we are not doing that right. We're not making an industry neutral standard. But also, we wanted to make it form factor independent, meaning that you could implement this in an integrated CPU package or a discrete package like an add-in card or such. When we bring the industry together like this, we get to innovate around the spec and add additional data acceleration features to the standard. And that's what we did. And this is kind of not a test of how quickly you can figure out which blocks go where, but it shows you the power of how we can boil it down to simple memory structures, and they're all in memory. The problem with accelerators is if you're doing some kind of a data movement, and if it stops in between, you don't know what it was doing when it stops in between. And that's something that is really useful for, say, someone like a virtualization vendor. If they want to do some kind of live migration, they want to know exactly when or how to pick up the data movement operation from in a new host. So it's easy to virtualize, is an architected function setup and control, and it's layered, meaning the inner shaded region is where all the data structures that a user space application needs to worry about, and the outer shaded region is what the privileged software controls. So you could, if you wanted to, you could mediate how user mode applications can do things, but at the same time, the user space has direct access to the accelerator interface while it's doing the data movement, right? And this is kind of like the best of both worlds. So while I showed you an SDXI function here, it's not specific to a PCI-based implementation. It's the DMA bus could be CXL or anything else that you want to implement with. But if you were sort of a PCI-based implementation, you could have various kinds of functions, a PF function or a VF function. Each of those functions can have multiple contexts to which a producer can enqueue work. And now we also
something like this replacing GPU direct storage, things of that nature?
I would kind of say that you could implement this in a GPU as well. You could implement this in a storage as well. And if both of them are trying to move this data, you could use some of these structures to be able to do that kind of work as well, right? The thing is, there could be more memory on the GPU side, there could be memory on the storage side. Someone else may be orchestrating the data movement, and they also want to do the memory-to-memory data movement. The storage itself might be trying to move the data from some memory space in an I/O device. And so all kinds of producers are possible. And the reason we call it producers could be software doing the work descriptor enqueuing. It could be anything that can provide those memory structures. Something else that we basically said is, okay, you can have multiple devices in one function group, and if you put them in a function group, you can move data between one context in one device to another context in another device. So that's also possible.
The transport could be PCIe, could be a memory bus, could be
Absolutely. It's anything.
CXL.
It could be CXL, it could be Ethernet. Like I said, it could be pigeons. Right. But and the idea is that we're basically trying not to uh, uh, make it specific to one kind of interconnect. Of course, if an interconnect provides certain kind of features like coherency or other kinds of PCI has certain kind of ordering which are desirable, then absolutely that it would make use of it. But if we don't specify a specific interconnect that you should be using for your DMA, and that's why it's pretty cool. I mean, there's one standard descriptor format that we are trying to align on. I mean, this goes into lots of details, but essentially you have a valid bit that tells you if the descriptor is valid. You have control fields that control how the descriptor enforces the ordering. For instance, for memory-to-memory data movement, it's sometimes very essential to put barriers or do things like syncing. Okay, make sure all the memory operations happened before this descriptor was launched. Or I want the write associated with my previous descriptor to finish before I start writing this descriptor's write. Example. Or I want to read on the buffer that has on the previous descriptor's write. Right. So these are the kind of important things that we want to put into the descriptor.
And the SDXI DMA engine is a piece of hardware?
Correct. So it is, if you really want to accelerate a data movement, then you would actually implement that in hardware. But at the same time, because you can virtualize it, you can have an emulated device as well.
So this is fitting very nicely with the whole CXL model.
Absolutely.
That's exactly where you're looking at being able to pay part of the, we can put hardware components on the CXL bus to help route memory access across systems. Okay.
Correct. I mean, so near memory, far memory, all of these kind of data movement can happen. But then even within a system with just DRAM, we have plenty of use cases. One interesting example is like virtualization vendors tell me, I want a VM to start with all buffer 0. And that's a really mundane operation, but it takes a long time if you have terabytes of memory. Imagine doing that for thousands of VMs and at the same time, and you're just taking up all of the CPU cycles for it, right? So you could use an accelerator to fill up a large buffer of memory with zeros, and that will be fine.
That'll be a short instruction set and offload. Okay, yeah, that's
correct. Or things like, hey, I want to just compress my memory or encrypt my memory and things of that nature. Or in some cases, they want to just do data movement between virtual machines, or in some cases, they want to move data into like storage memory or something of that sort.
How does this plug into security, zero trust, root of trust, those sorts of things?
Yes, absolutely. So the way security is built in is you get hardware protection through the IOMMU in a system. So as it's no different from, say, a NIC or a storage device trying to access memory. The problem with a NIC or a storage device maybe is that they're only using that as a source buffer or as a destination buffer, right? What this allows you to do is use the IOMMU both for the source buffer as well as for the destination buffer, right? And also, I mean, I will go into the next slide, which tells you on how we kind of protect these things, right? So this is a more complicated example of different address spaces that want to be part of this data movement. And in this example, address space B is orchestrating a data movement from address space A to address space C. So typically what will happen is it will enqueue a work into the descriptor ring. The function for that address space picks up the descriptor, reads that descriptor, finds an identifier for what is the address space that I'm targeting. In this case, the address space is A and address space C. In that A key identifier entry, there is an index for the lookup on address space A. And in that lookup, you match which function is actually allowed to do this data movement. And that's the security mechanism on address space A side. And even while you're reading the data from here, the IOMMU protects you from not being able to access if you're not allowed to access that data. The same thing happens when you're trying to do the DMA write on the other address space C. Right? So this is kind of the protection built in into the standard on you should be allowed to do this only if privileged software allowed you to do this type of data movement. Right?
A question from Michael here. How, I don't know if it's something yourselves have already kind of taken into consideration there, but in recent years we've seen these attacks such as Spectre and Meltdown where they've actually focused on speculative execution. And I'm just wondering what kind of mechanisms effectively this might impact, or effectively whether that's become part of the security design here to make sure that, as you've said, you're trying to validate, these accesses to memory, but then we see all these issues with speculative execution. It kind of breaks these walls down. Have you guys seen that? Have you tested for that at all?
No, so we haven't, this hasn't come up so much as a problem because in one way, this device is an IO coherent device at the moment. And we don't have a lot of the sideband attacks from cache that traditional CPU cores may have to deal with. So the IO coherency, as long as we maintain that from the DMA reads and the DMA writes point of view, we are not susceptible to those side channel attacks. But having said that, security is always a concern, and we look at it from which threat models that's this type of data movement covers and which it doesn't. One of the cool things that we are trying to do in the technical working group is also like, okay, I have memory space here and memory space here. What if this was a confidential memory region here and a confidential memory region here? Can I still affect the data movement in a secure manner? And that's one of the ways that we are trying to solve for those issues as well. Great question. And we're not stopping. I mean, we described the spec as how you could do this data movement from a cross-address space, but we also need some kind of a connection manager to help broker the connection so that the actual data movement can happen. And in the 1.0 spec, we kind of said that could happen in a sideband or a out of band path. But there is enough interest to make that into a standard as well. So that's where we're trying to look at the connection manager spec. Well, like I said, we are trying to look at different kind of operations that we might want to do as we are moving the data. Something of a light bulb that goes off to people is, okay, we discussed about how this could be an intra-host data mover. But with things like CXL, now you could have shared memory or pooled memory that is shared between different hosts. Now that makes this data mover a host-to-host data mover as well. At the same time, there are other people who also think that an SDXI function here, and an SDXI function here, the cross-function traffic or interconnect is not something that the spec is standardizing. So that could be something else as well. So from a host-to-host data movement point of view, that can also be possible if those functions are potentially in different hosts.
You can use RDMA.
What's that?
It can be RDMA.
Yeah, it could be RDMA. Yes, absolutely. Or it could be Ethernet, or it could be anything that you want to put as a fabric. And that's not what the spec is trying to standardize. The spec is trying to standardize on the memory structures on this side and memory structures on that side. And that's really neat. So we're trying to solve some of these problems in a more holistic way, right? And we're also looking at how we can develop the software in an industry standard way. So we are building a library called the libSDXI project. It's an OS agnostic user space library to help applications make use of this. There is an upstream driver the work is underway for it, and the community is helping enable those efforts. We're also looking at how we can provide emulation, SDXI emulation devices, not just for software, but also for virtualized implementations. And we're looking at how do we build a little bit of tooling around compliance with software and hardware interoperability. The last bullet that I had here was we also have a collaboration going on with the Computational Storage work group inside SNIA. because a lot of these, memory is everywhere. Memories is in a device, memories in the host memory. The part about making a memory-to-memory data movement accelerator is it actually cuts down the amount of data movement you need to do. It's kind of a little bit of wrapped thing. We are a memory-to-memory data mover, but we are also cutting down the number of memory data moves that needs to happen, right? And so this collaboration is envisioning SDXI devices in a computational storage architecture and looking at what are those features that are required to enable them as well. So 1.0 is released, the spec is out there. We are expanding the number of use cases that we're working on as well.
You figure you're going to have like a plug-in lab or a plug-in event or something like this for this? Is that how you would?
Yes, and that's one of the reasons the software group is working on the enablement activity, so we can create like these potential hackathons or plugfest kind of model. Go ahead.
No, just thinking about your comment on computational storage, does that lead me to the point of thinking that I could see this as a new storage transport protocol, from the idea that I've got CPUs in my SSDs that can be autonomous, and it could be an SDXI component in the bus?
That is certainly a good way of thinking about it. The thing is, memory and storage things are blurring.
Yes.
And a lot of the storage features are actually needed on the memory world as well. So what the standard allows you to do is, I can just imagine that you want to do snapshots. You might want to do replication, dual casting, multicasting. People come up with the different use cases that have traditionally been on the storage world. But a standard like this allows you to do that for the memory world as well. At the same time, on a philosophical note, different languages have different words that describe things beautifully. SDXI has been written for a memory world.
Yeah.
And that does allow you to do things in an interesting way from a memory point of view. But the worlds that are converging needs those features as well.
Okay, thanks.
At the beginning, you also mentioned the possibility to transform data or make computing. Seems now that is really promising in the part of copying, moving data.
Mm-hmm.
But how do you think to implement the transformation part? Which kind of computing power are you using? Because we'll be in this piece of hardware, and so will be maybe limited only on a few functions, or you think to interact with the computational part on the system to implement the transformation?
So it is possible to embed computation as you're moving the data. It is also possible to transform the data without a whole bunch of computation in between. And so the standard allows for both of that. And what I mean by that is an example of a transformation could be, okay, you might be just doing...
Yeah, it's clear, but where you take the computational power, because moving data is one part. You can make a chip very performance to do this. But if you have to add a computational part, then which language, which SDK is a lot of work. Or you just interact with the other computing part on the motherboard or on a DPU to make some kind of operation.
To begin with, it might be that we end up interacting with the computing element for a data move operation. And in the middle of that, it could be a pipeline of these kind of computations that get offloaded. But we're just getting started with the library work, the software work. So one of the good things about the community is that new ideas come in and they drive those use cases. And I see the scope available for those kind of paths as well.
Do you see like DIMMs of the future having this XDXI, CDXI, SDXI, DMA engine embedded in them? Is that?
I mean, certainly a use case is possible, but so with a standard like this, what it allows for people to look at is not everything is possible with certain kinds of hardware. Some things are really possible with other kinds of hardware. So, for example, bulk data movement may be something that some devices are really efficient at doing things. And it's not possible to build all kinds of hardware in certain kinds of general purpose computing hardware, right? But some of the operations can get offloaded to other kinds of devices as long as the cost economics work out for them to implement that. And if they're speaking the same language, then from an applications point of view, it's got a standard framework to work with. And that's where some of the innovations can come in terms of whether it's a memory vendor, it's an actual look-aside accelerator, or a compute a CPU that is actually implementing it. The innovations come in the actual implementations. We help make their things boring.
So one of the places that this would really come in handy is when we get into the idea of memory tiering within a host, where you have various different tiers of CXL memory, and you potentially want to promote or demote banks of memory from higher speed or higher latency to lower latency memory. And that's actually what I'm talking about in half an hour.
Yep.
Way to plug.
So I have a question. Since you brought up computational storage, right? So SNIA has a standard for computational storage. The API is there, and one of the things they talk about in the user mode stuff is the ability to copy memory to the host from the memory of the drive's computational storage section. And what I'm wondering is because you're having your own interface for doing memory, are you working with that group? And so when they call their memory copy, are they using your interface? I mean, is there a nexus where you guys meet here on the computational storage group?
Excellent question, because that's exactly what the subgroup that I talked about just here is working on.
Right.
And the southbound of the API could be an SDXI interface. And that could bridge the data movement from host memory to device memory. Or, so for example, you could envision an SDXI instance external to a storage subsystem. So in that case, you're doing the data movement from like host memory to storage memory. Or an SDXI instance could be internal to the storage subsystem, in which case it could still be doing host memory to storage memory, but it could also be doing data movement between different memory regions within the storage subsystem.
The call would be the same.
It could be the same call, yeah, correct. Or it could be as a result of the API, a series of pipeline operations that happen because of this interface.
Interesting, thanks.